Imagine a world where your computer doesn't hum with the heat of overworked silicon chips, but glows with the effortless speed of light. Sounds like science fiction, doesn't it? Yet right now, a company called Lightmatter is turning this vision into reality with a groundbreaking light-based computer that's poised to reshape the tech industry. Why does this matter? Because the way we compute today is hitting a wall. Silicon chips are struggling to keep up with the explosive demand for processing power, especially for artificial intelligence, AI. In this story, we'll dive into Lightmatter's Photonic revolution, explore why it's a game changer, and uncover what it means for the future of computing. Buckle up, because this is a tale of light, speed, and the next big leap in human innovation. To really grasp the significance of Lightmatter's work, we need to start with a problem. A quiet problem, yes, but one that's been looming larger and larger over the entire tech industry like a gathering storm cloud. It's what you could call the Silicon Crisis. For decades, since the very birth of the computer age, we've relied on this incredible material, silicon. Chip makers, the wizards of this tiny world, giants like AMD, like NVIDIA, they've followed a surprisingly simple, almost magical formula to boost performance. It was like a mantra. Double the silicon area, cram in more transistors, double the memory, and poof, you had more power, faster speeds, more capability. And honestly, it worked like a charm. This relentless doubling, this Moore's law writ large, has powered everything that defines our modern lives. Your smartphone? Built on this principle. The massive data centers that run the cloud, that host your emails, your streaming movies, your social media feeds, powered by this silicon magic. And critically, the jaw-dropping AI models that can now generate human-like text that fools us, or conjures stunningly realistic images from thin air. Yes, they too are built on mountains of silicon, but here's where the magic starts to get prohibitively expensive. That formula, double the silicon, double the power, it's running into some harsh realities. Today, a single, high-end graphics processing unit, or GPU, the kind essential for training complex AI models, can cost, well, it can cost more than your monthly rent, sometimes thousands upon thousands of dollars. Why? Because in the intricate microscopic world of semiconductors, you literally pay for every single square millimeter of that precious silicon. And those costs are not just increasing, they are skyrocketing. Think about it in a way we can all understand. Imagine you want to build a bigger house. Okay, naturally, a bigger house requires more land, more lumber, more concrete, more glass. It costs more money. That makes sense. But now, imagine that the price of land, the fundamental ingredient, keeps doubling every single year. Pretty soon, building any house, let alone a bigger one, becomes an impossible dream for most people. Only the ultra-wealthy, the biggest corporations with limitless budgets, could even consider it. That's essentially where we are today with silicon chips. The more we rely on this strategy of simply piling on more and more silicon, making the chips bigger, denser, more complex, the more unsustainable it becomes. And it's not just economically unsustainable, it's environmentally unsustainable too. Think about the data centers again. Those sprawling, anonymous buildings filled with blinking lights and server racks, quietly powering our digital world. The energy they consume is staggering. We're not talking about sipping power here. We're talking about gobbling it up at a rate that can rival the energy consumption of small countries. The heat they generate, the sheer amount of electricity needed to keep them running. It's immense. If we continue down this path purely relying on making silicon bigger and bigger, faster and faster, we are inevitably going to hit a hard wall. A wall where progress slows to a crawl. Not because we lack ideas for AI, but because we lack the fundamental computational power to bring those ideas to life. The incredible advancements we're seeing in AI today, they could stall. So the question becomes urgent. What's the solution? Do we just accept this future of slowing progress and escalating costs? Or do we need to fundamentally rethink computing? From the ground up, music becomes thoughtful. Host. And that is precisely where Lightmatter's light-based approach steps onto the stage. It's not an evolution of silicon, it's a revolution away from it. To really understand just how big a deal this is, let's zoom out for a moment and look at computing, especially at the scale needed for modern AI, at the scale of those massive data centers. At its heart, computing boils down to three fundamental pillars. Think of them as the three legs of a stool that holds up our digital world. Compute, interconnect, and memory. Compute. This is the raw brain power. It's how fast the chip can actually crunch the numbers, perform the calculations, solve the complex equations. It's the engine. Interconnect. This is the communication network. It's how all those different brains, all those individual chips, talk to each other, how they share data, how they coordinate their efforts. It's the nervous system and memory. This is where the data is held, where information is stored so the computer can access it quickly when needed. It's the workspace, the short-term and long-term storage. Right now, the vast majority of our computing power relies heavily on silicon for all three of these pillars. And guess what? Each single pillar, is facing its own distinct, painful bottleneck. Let's look at compute. The last decade in AI has been dominated by a specific kind of math, accelerated matrix math. This is the absolute backbone of deep learning, of neural networks, of how AI learns and processes information. GPUs, originally designed for graphics, turned out to be surprisingly good at this, and NVIDIA rode that wave. Google developed their own specialized chips, TPUs, to refine it further. And then came even more specialized chips, ASICs, designed to push efficiency to the absolute maximum for specific AI tasks. These are technological marvels, truly. But even these highly optimized engines, they are hitting physical limits. There's only so much matrix math you can cram onto a piece of silicon and run at speed without melting it or bankrupting yourself. Now, interconnect. Oh, the headache of interconnect. Imagine trying to coordinate thousands, sometimes tens of thousands of these powerful GPU brains all working on one giant problem, like training the next big language model. They have to exchange data constantly. They have to communicate their intermediate results. And even tiny delays in that communication, mere nanoseconds, billionths of a second, when multiplied across thousands of connections and trillions of data points, can slow down the entire process by hours or even days. It's like having a team of brilliant scientists working in separate rooms, but they have to pass notes under the door one by one. Frustrating, inefficient. And memory? It's a similar story of escalating costs and frustrating delays. Need more storage for your massive AI model? Okay, double the RAM. But remember our silicon crisis? Doubling RAM means doubling those skyrocketing costs. And even when the data is stored, accessing it, pulling it out of memory so the compute engine can work on it, is often a sluggish, time-consuming process compared to the lightning-fast calculations the chips are theoretically capable of doing. It's like having your notes in a filing cabinet across the room instead of right there on your desk. This is the landscape. A world of computing built on silicon, facing undeniable, compounding challenges across its core functions. And this is precisely the moment Lightmatter steps in. With a radical, elegant, almost disarmingly simple idea. What if we could use light, pure light, instead of electricity, to tackle these fundamental challenges? Light is faster, yes. It's more efficient, yes. But most importantly, it doesn't play by the same rules as electrons crawling through silicon wires. But to understand why light is so much more powerful for these tasks, we need to dive a little deeper. We need to peek under the hood, not just of a traditional silicon chip, but of this emerging world of photonic computing. You've probably heard the most basic claim. Light-based computers are faster because light travels faster than electrons. And that's true on a fundamental level. Light zips through a vacuum at roughly 300,000 kilometers per second. Electrons, while fast in their own right, move through wires much, much slower, more like drifting than zipping when you consider their overall progress. But, and this is a crucial but, the real genius, the profound advantage of photonic computing, lies not just in the speed of travel, but in what happens along the way. Let's look closely at a traditional silicon chip again. Imagine that AMD or NVIDIA GPU. Inside it, you've got billions, truly billions, of tiny structures called transistors. Think of them as incredibly small, incredibly fast switches. They are the fundamental building blocks of digital computing, constantly flipping between an on state, representing a 1, and an off state, representing a 0. This flipping, this dance of zeros and ones, is how digital chips perform calculations. But every single time one of these tiny transistors flips, it has to do something physical. It has to charge or discharge a tiny capacitor. Think of a capacitor like a miniature bucket that holds an electric charge. When the switch flips one way, the bucket fills. When it flips the other, it empties. This process, filling and emptying these microscopic buckets of charge, takes time. We're talking about nanoseconds. Yes, billionths of a second, which sounds incredibly fast. But when you consider that this has to happen billions of times per second, across billions of transistors, that's where the slowdown creeps in. It's not just the speed at which the electrons could move. It's the constant stopping, starting, filling, emptying that bogs the whole system down. It's like trying to drive across a city with a traffic light on every single corner. You spend more time waiting and accelerating than actually moving. Now, enter the world of photonic chips. Lightmatter's chips. These are fundamentally different. They are, at their core, analog, not digital. And that distinction is a game changer, of monumental proportions. Instead of relying on billions of switches flipping between discrete zeros and ones, photonic chips use light waves, the continuous flowing energy of light, to process data. And here is the critical part. Light doesn't need to stop to charge capacitors. It doesn't need to wait for a bucket to fill or empty. It flows continuously, effortlessly, like a river moving downstream. This means that computations, the actual mathematical operations, happen on the fly. As the light moves through the chip, the calculations are being performed simultaneously without the stopping, starting, and delays that plague digital silicon chips. Furthermore, light operates at incredibly high frequencies. We're talking terahertz frequencies. That's 1,000 times higher than the gigahertz frequencies that electronic chips typically operate at. This higher frequency means that light has the capacity to carry and process massive amounts of data simultaneously. Remember our traffic light analogy? Photonic computing is like a highway with no traffic lights, where cars, the data, not only zoom along continuously, but can also travel in hundreds of parallel lanes on the same road at the same time. And this brings us to the heart of the magic, the secret sauce that makes photonic computing so perfectly suited for the demands of AI. It all comes down to physics, specifically Maxwell's equations. These are the fundamental laws of physics that describe how light, how electromagnetic waves behave. And here's the incredibly useful part for AI. These equations, in many of their forms, are linear. Why is linearity exciting? Because the absolute core, the fundamental building blocks of almost all modern AI algorithms, are linear operations. Additions, and multiplications. Think about neural networks. They are essentially layers upon layers of matrix multiplications and additions, followed by some non-linear steps. And light, governed by Maxwell's linear equations, performs these additions and multiplications naturally. As light waves interact, they literally interfere with each other in ways that correspond directly to multiplication and addition. It's like the math is baked into the very fabric of how light works. Let's break this down with a concrete example, one that Nick Harris, Lightmatter's co-founder and CEO, often uses. Say you need to perform a matrix multiplication, multiplying two grids of numbers together. This is a common computationally intensive task in AI. Imagine a relatively small, say a 128x128 matrix. On a traditional, state-of-the-art GPU, performing this task might take something in the realm of 100 nanoseconds, 100 billionths of a second. That might sound fast, and it is. But it requires many clock cycles, many billions of transistor flips, many filling and emptying capacitors. On Lightmatter's Photonic processor, the same task, that same 128 matrix multiplication, takes just 200 picoseconds, 200 trillionths of a second. Let that sink in for a moment. 100 nanoseconds versus 200 picoseconds. That's a speed up of, get ready for it, anywhere. From 100 to 1,000 times faster. Why such an astronomical difference? Because, as we discussed, the light-based chip isn't wasting time switching transistors. It's not waiting for capacitors to charge or discharge. The computation is the movement of light through the chip. It's like comparing a bullet train that never stops between stations to a horse-drawn carriage that has to pause and reload passengers at every corner. The fundamental mechanism is just orders of magnitude more efficient for this specific type of work. But the advantages don't stop at raw speed. Remember how light operates at higher frequencies? This means it can carry more data simultaneously. Lightmatter leverages a clever technique borrowed from fiber optic communications called wavelength division multiplexing, or WDM. This is a fancy way of saying they can use different colors of light, all traveling through the same tiny channel on the chip, to process multiple independent data streams in parallel. Imagine a single fiber optic cable carrying hundreds of different TV channels or internet signals at the same time, all distinguished only by the specific color of light they're using. That's the kind of parallelism they can achieve. This means they can process vastly more data without needing more physical chip area and without needing proportionally more power. This incredible efficiency isn't just about making AI faster. It could fundamentally slash the energy demands of those power-hungry data centers, making AI not just a marvel of speed, but also significantly greener, more sustainable. Now, with all this talk of analog computing and continuous light flow, it's time to address the elephant in the room, the big historical challenge that has kept analog computers in research labs for decades. Precision. Let's be honest, digital chips with their absolute unambiguous zeros and ones have always been the gold standard for accuracy. Think of a digital measurement as using a high-precision ruler with perfectly defined markings. You get an exact reading every time. Analog chips, on the other hand, operate on continuous values, not discrete steps. Historically, they've been more like estimating distances by eye or using a ruler with smudged, blurry markings. You get a sense of the value, but not the pinpoint accuracy. Until recently, this inherent imprecision made analog computing unsuitable for any task requiring high fidelity. You wouldn't want your bank account balance to be rounded off due to an analog chip's estimation, right? You wouldn't want a critical medical calculation to be slightly off. And for complex AI models, where tiny errors can compound across millions or billions of calculations and lead to wildly incorrect results, that lack of precision was a non-starter. This analog challenge, it was a fundamental barrier. But this is where Lightmatter has truly performed a feat that is nothing short of revolutionary. They've cracked the code. Their new photonic chip achieves a level of precision remarkably close to that of a 32-bit digital chip, the kind of precision used in many demanding applications. How in the world did they do it? When I had the chance to speak with Nick Harris, Lightmatter's CEO, he shared their elegant solution. It's complex physics and engineering, yes, but the core idea is brilliant in its simplicity. We've developed a unique number format that works perfectly with our photonic cores, Harris explained. We call it ABFP16. Okay, ABFP16. Sounds technical, but the concept is quite practical. Think of it like this, going back to our baking analogy from the article. If you need a very precise amount of flour for a delicate recipe, you don't try to count every single grain. That would be digital and impossible. Instead, you use a good scale. Lightmatter's ABFP16 format works similarly. Harris explained, we essentially assign a scale, a multiplier, to a block of numbers that we're about to send into the photonic core. We factor out that scale, handle that scaling factor using a tiny bit of digital processing on a companion chip, and then we send the numbers without the scaling factor into the photonic core. It's like telling your helper in the kitchen, okay, this recipe needs 3.7 cups of flour. The scale says we need 3.7 times this base amount. You tell the helper what the base amount is and what 3.7 is. Then you hand the helper a simple task. Measure out the base amount and then multiply that by 3.7. The helper, the photonic core, does the multiplication quickly and efficiently using the light waves. Harris continued, the photonic tensor core, that's where the light does the heavy lifting. It handles the additions and multiplications incredibly fast, in analog. The result of that light speed calculation comes back to the digital side, and we simply apply the original scale back to the result. And voila! By carefully managing the magnitude of the numbers on the digital side before and after the photonic calculation, they achieve near-digital precision for the overall operation. It's using the strengths of both worlds. Silicon for the precise scaling and management, and light for the blazing fast, energy-efficient core computation. They also use other clever engineering tricks. For instance, they amplify very small signals within the photonic chip to make sure that crucial details, the kind that neural networks rely on, aren't lost in the noise or inherent slight variability of analog light signals. It's like turning up the volume on a quiet whisper you need to hear clearly. This breakthrough is monumental. It means photonic chips aren't relegated to niche, low-precision tasks anymore. They can now run complex workloads, from training AI to play Atari video games to running significant portions of large language models, with an accuracy that genuinely rivals traditional digital systems. And critically, it means existing AI models, often trained with 32-bit or 16-bit precision in mind, can potentially run on this new hardware without needing massive retraining or complicated, performance-killing translations. That plug-and-play compatibility? That's a huge accelerant for adoption. So what does this revolutionary photonic engine actually look like? Let's peek inside the box. Lightmatter's current processor isn't just a photonic chip floating on its own. It's a brilliant hybrid design. Picture a single package, but inside it's a carefully orchestrated stack of chips. There are 2 electronic silicon control chips on top, like the conductors of our orchestra, and below them are 4 photonic tensor cores, the virtuoso light performers, all connected by incredibly high-speed links. This hybrid approach is key. The silicon electronic chips handle the tasks that digital computing is still best at. The non-linear math, the complex logic operations, the control signals, and now, thanks to ABFP16, the precise scaling of numbers. Meanwhile, the photonic cores? They are unleashed to do what light does best: the heavy lifting of linear operations, those matrix multiplications and additions, at unparalleled speed and efficiency. It's a partnership, playing to the strengths of each system. Let's focus on one of those photonic cores. How does it work? It's light magic. Data, the numbers that represent things like the pixel values in an image, or the weights in an AI model. This data is first translated or mapped into the optical domain. This means the electrical signals are converted into light waves, where the intensity or phase of the light represents the value of the number. These light waves then embark on a journey through the photonic chip. They travel through tiny, precise channels etched onto the chip's surface called waveguides. Think of them as miniature rivers guiding the flow of light. Along these waveguides, the light passes through sophisticated devices called Mach-Zehnder, interferometers, or MZIs. These are fascinating structures. By carefully controlling the path of the light through the MZI, engineers can use the interference patterns of the light waves to perform mathematical operations, specifically multiplication. The data-carrying light wave interacts with another light wave that represents the weight you want to multiply by, and the output light wave's brightness, or intensity, directly represents the result of the multiplication. This happens simultaneously, for thousands, even millions of calculations across the chip. The light waves, now carrying the results of these multiplications, continue their journey. At the end of the computation path, these light waves arrive at photodetectors. These are devices that convert light back into electrical signals. And here's another piece of physical elegance. As the light waves carrying different multiplication results arrive at the same point, their energies naturally sum up. This means the complex process of summing up many multiplication results, another core operation in AI, happens automatically, instantaneously, in the optical domain, without needing extra steps or energy in the electrical domain. The electrical signal produced by the photodetector represents the final computed value, and it's sent back to the digital control chip for further processing, applying that scale factor from ABFP16, or feeding it into a nonlinear function. And remember, this entire process, from data entering the photonic core to the result emerging as an electrical signal, takes that blistering 200 picoseconds. What's truly mind-blowing is looking at the sheer scale packed into one of these hybrid chip packages. We're talking about 50 billion transistors on the silicon side, working in concert with 1 million photonic components on the light side. It's not just a chip, it's a complex, futuristic orchestra of light and silicon, where light takes the lead on the most demanding numerical symphonies, and silicon provides the precise rhythm and structure. The result? A computing engine that is not only orders of magnitude faster for AI tasks, but also incredibly energy efficient. Lightmatter is demonstrating performance levels of hundreds of teraflops, trillions of operations per second, per watt of power consumed. Compare that to traditional GPUs, and you see a path towards drastically reducing the energy footprint of AI, which, as we noted earlier, is becoming a critical global concern. While the photonic processor itself is undoubtedly a star, Lightmatter isn't just focused on the compute part of the puzzle. Remember those three pillars? Compute, interconnect, and memory? They are also tackling the critical interconnect bottleneck head-on with a product called Passage. In today's massive AI data centers, we have thousands, sometimes tens of thousands, of powerful GPUs. But their collective power is limited by their ability to talk to each other, to share the results of their calculations, to stay in sync while training a giant model. As we discussed, these connections largely rely on traditional copper wires and electrical signals. And copper, while reliable, has its limits. Electrical signals lose strength over distance. They interfere with each other, and sending them requires significant power. They are, in essence, the slow, congested dirt roads of the data center world. Even a tiny delay, a nanosecond spent, waiting for a signal to travel or for congestion to clear, adds up quickly when you have millions of signals crisscrossing a data center network simultaneously. This is the frustrating interconnect bottleneck, and it's a massive hurdle for truly scaling AI to its full potential. It's like having a factory full of brilliant workers who spend half their day waiting for materials to be delivered, or for their colleagues to pass information along. Passage is Lightmatter's revolutionary solution to this problem. It replaces those slow, power-hungry copper connections with, you guessed it, light. It's like ripping up the dirt roads and laying down high-speed fiber optic rail lines between every single worker in the factory. Passage isn't just a little faster. It's capable of delivering astonishing amounts of bandwidth. The sheer volume of data that can move through the connection at any given moment. We're talking up to 64 terabits per second of bandwidth with their initial systems. That's 8 to 10 times faster than competing electrical interconnect technologies. Their M1000 platform pushes even higher, demonstrating 112 terabits per second. And they are already building systems running at 60 terabits per second. To really wrap your head around that number, 60 terabits per second. Imagine simultaneously streaming millions of high-definition 4K movies all at once through a single connection, without a single stutter or buffer. That's the kind of data fire hose we're talking about. Why does this matter so profoundly for AI? Because faster interconnects mean the powerful GPUs or photonic processors spend far less time sitting idle, waiting for data to arrive from other chips. They can keep their engines running at full throttle. This drastically slashes the training times for massive AI models. Think about those advanced AI models that are designed for complex reasoning, like DeepSeek R1 mentioned in the article. Currently, asking such a model a detailed question might take 10 minutes or more to generate a thoughtful, multi-step response as it retrieves and processes information from different parts of the network. With the kind of blazing fast photonic interconnect that Passage provides, the time spent waiting for that internal communication could plummet. That 10-minute wait could potentially drop to just 10 seconds. This isn't just a technical speed-up. It changes the user experience of AI. It makes advanced AI feel more responsive, more interactive, more intelligent. Furthermore, like their photonic processor, these light-based interconnects use significantly less power than their electrical counterparts. Fewer watts consumed means lower operating costs for data centers, and, crucially, a smaller energy footprint. It's a powerful combination of enhanced performance and increased sustainability. So we've talked about compute, revolutionized by the photonic processor. We've talked about interconnect, revolutionized by Passage. That leaves one final crucial piece of the puzzle: memory. In computing, especially complex AI tasks, you constantly need to store intermediate results. You do a calculation, get a number, and you need to remember that number to use it in a later calculation. In traditional digital silicon chips, this is handled by those tiny capacitors we talked about earlier. They hold an electric charge, effectively, storing the 0 or 1 value. Photonic chips, at least in their current form, don't have a direct, elegant equivalent to this. Light flows. It doesn't easily just stop and hold a value in the same way an electrical charge can be trapped in a capacitor. Photonic chips excel at processing data as it moves through them, but they struggle to inherently remember that data once it has passed. Right now, Lightmatter's system and most other photonic computing approaches deal with this by converting the light signals back to electrical signals and then storing those electrical signals in traditional digital memory. This works, but it's a bit of a bottleneck. The conversion process takes time and consumes energy. It's like having a lightning-fast brainstorming session, the photonic compute, but then having to slowly write down every single idea in a notebook by hand before you can use it again, converting to digital memory. It slows down the overall process, and adds complexity and power consumption. This memory challenge is one of the hot topics, one of the key frontiers, in the entire field of photonics research. It's not something Lightmatter or anyone else has fully solved with light yet. While it's not the primary focus of their current product revolution, which targets compute and interconnect, it is a significant hurdle that the field as a whole will need to clear to realize the full end-to-end potential of light-based computing. Imagine a future, perhaps still a few years away, where photonic memory exists, where light-based chips could store data as effortlessly and efficiently as they process it, all without leaving the optical domain. That would be another monumental leap. It's still a ways off, still in research labs, but companies like Lightmatter, by pushing the boundaries of what's possible with light, are laying the essential groundwork for such breakthroughs. They are building the ecosystem, the fundamental understanding, that will make true photonic memory possible down the line. But let's be clear, even without a perfect photonic memory solution today, Lightmatter's achievements are incredibly significant, and they are just the beginning. Their photonic processor isn't a theoretical curiosity. It's a working piece of hardware that can already run demanding AI tasks. They've shown it running DeepMind's Atari games, demonstrating its ability to handle complex reinforcement learning. They've also shown it running NanoGPT, a well-known language model with 100 million parameters. A significant AI workload, and here's a crucial point for the industry. They can do this without needing developers to completely rewrite their AI models, without needing complex, performance-killing model translations, and without requiring extra training specifically for their hardware. It's remarkably compatible. This plug-and-play capability, allowing developers to use existing AI frameworks like PyTorch or TensorFlow with Lightmatter's hardware, is a huge deal for making this revolutionary technology accessible and accelerating its adoption. Looking ahead, the potential for scaling this technology is immense. Remember wavelength division multiplexing, using different colors of light? Right now, they might be using a few colors, but the physics allows for many more. By using multiple colors of light, perhaps up to 16, 32, or even more simultaneously, traveling through the same waveguides, they can exponentially boost the amount of data processing happening in parallel, all without increasing the physical size of the chip or significantly increasing the power consumption. It's like adding more and more lanes to that high-speed light highway without needing to widen the road. Their work on interconnect is also rapidly evolving. Lightmatter has announced their Passage L200 product, expected to launch in 2026. This next generation is projected to offer 32 or 64 terabits per second of bandwidth per link. This kind of insane connectivity is what will be needed to truly unlock the power of massive GPU or photonic processor clusters, allowing tens of thousands of chips to act as a single, cohesive, incredibly powerful supercomputer. Analysts are starting to take notice, and the predictions are bold. Some forecast that by the end of this decade, by 2030, photonic technologies like those pioneered by Lightmatter won't just be a niche curiosity. They will dominate huge segments of the computing landscape. They could become foundational for advanced AI, reshape the entire telecom infrastructure, and even play a crucial role in the development of quantum computing. We are potentially witnessing the dawn of a new era powered by light. But perhaps the most exciting promise of Lightmatter's work isn't just about mind-bending speed or staggering efficiency. It's about the potential to democratize AI if computational power becomes significantly cheaper and less energy-intensive. It could lower the barrier to entry for developing and deploying advanced AI. Imagine a world where small startups can afford to train cutting-edge AI models without needing billion-dollar data centers. Imagine a world where those data centers, which are essential infrastructure, consume a fraction of the energy they do today, potentially running entirely on renewable sources because their power demands are so much lower. That That is the profound promise of photonics. It's a path towards AI that is not only more powerful, but also more accessible, more equitable, and more sustainable for our planet. So, what's the takeaway from Lightmatter's incredible story? Beyond the physics, beyond the engineering, beyond the sheer technical marvel, what can we learn? For me, the core lesson is about daring to question the status quo. For decades, silicon has been king. We've built our entire digital world on its back. It has served us astonishingly well. But as its fundamental limits become clearer, as the challenges of cost and energy become undeniable, innovators like those at Lightmatter aren't just trying to squeeze a little more life out of the old way. They are showing us that there is another way entirely, a radically different path. They remind us that true progress, the kind that reshapes industries and changes the world, often comes from embracing the unfamiliar. It comes from looking at a problem everyone else accepts as a constraint and asking, what if there was a completely different material, a completely different physical principle we could use? Here's a practical connection, something we can apply to our own lives. Think about a challenge you're facing right now. Maybe it's a difficult project at work, a stubborn personal habit you want to change, or a problem in your community that seems impossible to solve. When you hit a wall, when the usual approaches just aren't working, when you feel like you're just pushing harder and harder against something immovable, don't just keep doing the same thing. Don't just try to double down on the silicon you're already using. Step back, take a breath. Question the fundamental assumptions you're making about the problem. Are you trying to solve it the way it's always been solved? Are you limited by thinking within a particular box? Look for a new path. Ask, just as Lightmatter asked, what if there's a completely different way to do this? What if the solution uses a completely different material, a different approach I haven't even considered? It's not easy. Shifting your perspective is one of the hardest things we can do as humans. It takes courage to abandon the familiar and step into the unknown. But Lightmatter's story, illuminated by the very light they are harnessing, shows us that this is how breakthroughs happen. This is how revolutions begin. So, I'd love to hear your thoughts on this. What do you think about the potential of light-based computing? Could photonics be the key to unlocking the next generation of truly transformative AI? Or are there other technologies, other revolutionary ideas that you're incredibly excited about? Drop your thoughts in the comments below. Let's keep this fascinating conversation going. I truly value your perspective. And if you found this deep dive into the dawn of light-based computing as mind-blowing as I did, do me a favor. Share this story with a friend, a colleague, anyone you know who loves thinking about the future of technology and innovation. Let's spread the word, spread the light of this incredible breakthrough together. Before I sign off, I want to offer you my sincere wish for good health, for you and your loved ones. And as we continue our journey exploring the frontiers of science and technology, I wish you endless curiosity. Never stop asking questions. Never stop looking for new ways. If you enjoyed this story and want to join our community of tech explorers, hit that subscribe button. We've got more mind-bending stories, more glimpses into the future, coming your way very soon.